Hello everyone and welcome back to the chapter of Thermodynamics. So in this particular video session, we will be taking a look into the relationship between Cp and Cv through an enthalpy change expression. That will be our first point of the discussion for today. Followed by how do we experimentally calculate or experimentally get to know the internal change and the change in the enthalpy of a particular reaction. So those particular things we are going to study under the calorimetry as a process. Okay, so let's start with our first thing for this video session, and that is going to be the relationship between Cp and Cv. And this particular relationship we are going to derive it using the enthalpy change expression, that is through change in enthalpy expression. Alright, so first, in order to come across the Cp and Cv, let us first consider a simple system which is going to take in Q amount of heat. Okay, so let's consider that we have a simple system over here. Okay, so to this particular system, let us say that this is the area or the position of the piston. Let's say this is a piston that we are keeping over here, and let's say that this particular area is being covered by the gases. Alright, quite simple. So let me say that this particular system is going to absorb Q amount of heat. So we are supplying Q amount of heat to this particular system. Correct. So as we supply Q amount of heat to the system, depending upon the condition, whether the system is kept at the constant volume or whether this entire process has been occurring at the constant pressure, we are going to have two different type of expressions. Correct. Let us say, first point, at constant volume, if I am going to supply this at the constant volume. Okay, so at the constant volume, the amount of heat that we are going to give or supply to the system, let us give it as Q. So Q is equal to Q, the heat supplied at the constant volume. This should be equal to Cv. Cv is the heat capacity at the constant volume into the change in the temperature that occurs. Correct. So let us say that this is our first point. Suppose to this same kind of system, if I am going to supply the heat, but this is going to be at the constant pressure. This is going to be at the constant pressure. Alright. So that is nothing more than Q is equal to. So at this particular point, the things change as the heat supplied is nothing more than the heat supplied at the constant pressure is equal to Cp into delta T. Let us say that this is a point number 2. Correct. So now, can we say that the heat supplied at the constant volume is nothing more than the change in the internal energy? This is first point what we have already deduced in our previous lectures. Correct. Now on the other hand, what do I know is the heat supplied at the constant pressure will result in the change in the enthalpy. Okay, so let us keep these 2 points ready over here. Okay, so from the ideal gas equation, as we have taken our gas over here, let's consider the gas that we have taken is an ideal gas. So therefore, for this particular expression, PV is equal to N into R into T. Okay, so if I am going to take 1 mole of gas, okay, so if I am saying that 1 mole of gas, N is equal to 1, this is what I will understand. Correct. So therefore, if N is equal to 1, then can we say that therefore P into into V is equal to R into T. Let us keep this thing ready. Let's say this is our third expression. Alright. So, from the enthalpy change, okay, from the enthalpy change expression, what do I know is delta H is equal to the delta U plus of P into delta V. This is what expression I already know. Correct. So this is an expression for our enthalpy change. Now, what shall we do is, we will try to take this delta outside. If that happens, then can we write it as delta H is equal to delta U, correct, plus delta P into V. Okay. Now, what shall we do is, we'll take this expression. So what we have here, P into V. But P into V is equal to R into T as per as the equation number 3. Correct. So substituting PV is equal to RT. Okay. So if we do substitute that, then we are going to end up getting delta H is equal to delta U plus of delta R into T. Is this correct? Now, what we understand over here is R into T, this particular product, is nothing more than the universal gas constant into temperature. Universal gas constant. Now, that particular figure, that particular magnitude remains constant, correct? So, what we can change is with respect to temperature. So, if I take this particular delta inside, it will affect only the temperature. So, therefore, let us say that this particular expression becomes as delta H is equal to delta U plus of R into delta T. This is how it becomes. Now, coming back to these two expressions as what we have already. So, delta U is equal to QP. So, therefore, QV is equal to, I'm extremely sorry, it should be QP is equal to QV plus of R into delta T. Is this correct? But what we know about QP? QP is nothing more than CP into delta T. So therefore, we'll take this expression over here. CP into delta T is equal to CV into delta T. Okay, into, sorry. So that is going to be as plus of R into delta T. Right? So, what expression that we have common in this all terms is going to be delta T and delta T. So, we can take off the common from here and we can cancel out with this one. So, what remains with us is going to be as Cp is equal to Cv plus of R. This is going to be for 1 mole of gas. Okay, now if we consider it to be as n number of gas, then this particular expression we can give it as Cp is equal to, okay, Cv plus of n into R. So this is for the n number of moles of gases. So this is the relationship between Cp and Cv. Okay, so let's go with the next concept. Our next point of study is how to measure the delta U and the delta H of a particular reaction. Okay, so whether we are trying to determine the change in internal energy or whether we are trying to determine the change in the enthalpy. In short, we are looking at what is a change of the energy that has been caused in this particular system. Correct. So, whenever we are looking at the change with respect to energy of a particular reaction, these change of energy in a particular reaction are measured by certain experimental techniques. And these experimental techniques, which will help us to determine these energy change, we call it as calorimetry. Okay, we call it as a calorimetry. Now, why? The device that we use use in order to calculate the change in energy, whether the change in enthalpy or change in internal energy is concerned, that particular apparatus, okay, so those particular apparatus, we call it as calorimeter. Okay, so calorimeter is the apparatus which is going to help us in order to determine the change in the energy, while the experimental procedures, the techniques are called as calorimetry. Okay, so I hope you understood the difference between these two. Now, there are different types of calorimetry. Okay, now in order to determine delta U, we use a special type of calorimeter which we call it as the bomb calorimeter. Okay. Now, before entering into this particular bomb calorimeter, let me tell you that how do they basically determine everything? What is the general procedure? Let's understand that. So first thing, what they do is they first take the apparatus, your calorimeter, okay, and they first know what is the specific heat of this particular calorimeter, right? So this calorimeter is an apparatus. Now they take this apparatus which is going to contain your substance which is undergoing the process. Now they take that and they immerse, this apparatus is immersed, they dissolve it inside, they immerse it inside a particular type of liquid, any known liquid they take. Okay, and after that, whatever the process is going to start, it is going to start in this particular calorimeter. As the process starts, that particular calorimeter either is going to give away the energy or either it is going to absorb the energy from the surrounding. Depending upon that, we can see the temperature difference in this liquid. Okay. So, if the liquid is going to become hot, we shall understand that in the process in the calorimeter is giving away the energy. So, exothermic reactions. If this particular liquid, what we have, it is going to become colder, that means this particular liquid is giving the energy to the system. So, endothermic reactions. So, whether it is endothermic or whether it is exothermic, it is going to affect the temperature of this liquid. So, understanding what is the change in the temperature, they will first figure out the specific heat of this liquid also. Okay, so as they understand specific heat of the liquid, they already know what is the specific heat of the calorimeter, they will understand what is the change in the complete energy that has occurred in the calorimeter in that particular process which is occurring in this particular calorimeter. Okay, so I hope you understood the general procedure. So let's understand that taking a particular bomb calorimeter into consideration. Let us first understand how do we calculate the change in the internal energy. So here, we are trying to determine the change in internal energy, right? So the change in the internal energy, that is nothing more than the delta U. Now, delta U, that means the heat which is involved in this particular process is going to occur at a constant volume. Correct? We have that expression as QV is equal to delta U. So, whatever the heat changes that occur in this particular process, all of them occur at a constant volume. Remember this. So, in this case, the entire process, as what we have, it occurs at constant, okay, at the constant volume. This is the first point that we need to understand. So, any process that is occurring at a constant volume, and if we want to check the change in the internal energy, then that particular thing is done by the apparatus which we call it as the bomb calorimeter. Okay, so this particular bomb calorimeter is something like this. Okay, now please follow this outermost black line that you see. This outermost black line is nothing more than a simple vessel. Okay, and this vessel over here is going to contain water. Okay, this is completely filled with water. As we have discussed in our previous section that we are going to take the calorimeter and we are going to immerse it in water or a particular known liquid. So here the liquid that we are taking is going to be water. So our main shell is inside this. That is this particular line that you see, black line, that will represent to us the actual vessel wherein the reaction occurs, and that particular vessel we refer it as the bomb. Okay, now how do they do it? Okay, now try to understand this. The bomb is taken and it is immersed in water. In this particular bomb, they are going to keep a combustible material or a combustible substance. So if you can see this red color one over here, this is going to be a combustible. It is going to be the combustible substance. Okay, so this is a substance which is going to be combustible. I hope you people can see that there are two lines which are connecting to this. These are actually the firing lids, okay, which are responsible for burning. So these are our firing lids. Okay, so now this green color one is nothing more than a simple thermometer, which is going to indicate to us what is the change in the temperature that has occurred. Okay, so now I hope you people can see that there is a small opening over here that is at this particular point. This opening is through where we are going to send oxygen inside. So this is our oxygen inlet. Okay, and finally here we have a stirrer. Okay, this is our stirrer over here. So any particular process which is going to occur at the constant volume, that means this entire system is sealed. The particular volume is not going to expand over here, correct? So once we have taken this bomb and it has been immersed in water, these firing legs are connected to battery. Okay, so when we switch on the electricity, these firing rods will start to burn this material inside the bomb under the presence of oxygen. So as a result of which this particular substance is going to burn, but the volume is going to remain the same because this entire thing is occurring under the constant volume. Now as a result of which the heat is going to be immersed out, correct? The heat evolves out. In order to see the heat is not lost to the surrounding, in order to check what exactly the change in temperature is, we are taking the help of water in this. Okay, so it has been immersed in water bath, you can say. As a result of which you will see the change in the temperature that has occurred in water. So measuring the change in the temperature of water, we can calculate how much amount of heat that has come out. By the expression, first when you understand how much is the temperature change. So once you understand what is the temperature change, you will get, let's say temperature change over here is delta T. Alright, so now we can say that Q, that is nothing more than the heat is equal to, okay, so heat capacity of this particular system into mass of this particular combustible material is M into the delta T. Okay, to be much more specific, as we are looking at how to calculate the change in the internal energy, correct? Now, using this expression, as we know that the heat is supplied at the constant volume, so therefore we can change this expression as delta U is equal to, okay, so is equal to C, the capacity of the system, into delta T, that is a change in the temperature that has occurred, into M. Capital M refers to the molar mass, the whole thing divided by, okay, M. Smaller m refers to the mass of the substance. Okay, so this is how bomb calorimetry works. Okay, so bomb calorimetry is helping us in order to get the value of change in the internal energy. Okay, so let's start with the next one, that is going to be how do we calculate the change in the enthalpy is concerned. Now let us understand as how do we measure the change in the enthalpy for a particular reaction. So in order to determine the change in enthalpy. Okay, so when does a change in enthalpy occurs? When the particular reaction either is going to take in the energy or either it is going to give out the energy in form of heat at a constant pressure. So every single thing is occurring at a constant pressure over here, correct? So the heat exchanges are going to occur at a constant pressure. So here, the first thing that we have to note is the entire reaction is supposed to happen at a constant pressure, right? So here, so at the constant pressure, what we do is we are going to take a particular reaction. Let's say this is a reaction system that what we have taken. Now this outline that you see of a cup, this outline of a cup is called as the polystyrene cup. Okay, and in this cup we are going to take the reaction. Let us say that I have taken in this cup water, and to this water I am going to add a small amount of sodium to it. So what is going to happen? Generally the reaction starts, sodium starts reacting with water and the energy is going to be given out. Correct. Now that energy that is going to come out in the form of heat, we are going to measure that with the help of a thermometer. So we are going to keep a thermometer over here, check the temperature difference, quite simple as that. So whatever the temperature difference that you get, you can directly calculate the heat change. Okay, so in this case, the direct relationship is that QP is directly related with the change in the energy. Correct, that is a change in the enthalpy. So here is where you can see that the reaction occurring. So now depending upon the reaction, we have two types. Either the reaction can be an endothermic or whether the reaction can be an exothermic. So if the system, if this system loses heat, that is the heat is coming out of the system going to the surroundings. So in this particular condition, what is going to happen is, whatever the QP is there and the delta H for this particular reaction, these two things are going to be negative. Okay, so this happens when we have an exothermic reaction. Okay. On the other hand, if this particular system is going to absorb the energy from the surroundings, so at that particular time, if it absorbs energy, that is in the form of heat, of course, so in that particular condition, our delta H and our QP are going to be taken as positive. So these are the things occurring for an endothermic reactions. Alright, so for an exothermic reaction, QP and delta H are going to be taken as negative, while for the endothermic reaction, we have the QP and the delta H as positive. It's quite a simple process over here. Okay, so let us end this particular session over here. Thank you for watching. If there are any doubts, you can contact us. Take care.